This video is about logistic growth, which is something you saw in pre-calc, but we'll be looking at it from a calculus point of view. So rather than getting straight to the formula, let's try to derive where it comes from. So we're going to imagine a problem in which something is spreading in a way that would be similar to logistic growth. So let's imagine we have a university with 20,000 students and two of them know some piece of gossip. And we'll imagine that if someone knows this piece of gossip, he tells it to another student at an average rate of one person every 2 days, which we can think of as on average half a person per day. And we'll assume that when you tell someone, it's completely random, that it could be anyone from the university, and maybe they've heard it before and maybe they haven't. So we want to set up a differential equation and then solve it. So let's call this function g. So g of t is the number of people who know this piece of gossip at time t measured in days. And we know that g of 0 is equal to 2. So we want to think about how this grows. So let's make this concrete. Let's imagine, what if 2,000 people know? And let's think about the rate at which this gossip would be growing. So 2,000 people know, but they're sharing it at half a person per day. So what that means is probably there are going to be 1,000 shares of this piece of gossip. 2,000 people know it. On average, half of them will share it in a day. So we're imagining it gets said 1,000 times. But keep in mind, it's not always being said to people who are hearing it for the first time. Some people who are hearing it already know it. So we need to think about what portion of people will be hearing it for the first time. And what we know is right now, we have 2,000 people know and 18,000 people don't know. So what that means is 90% of the population don't know it yet. So if we have people who are hearing it at random, right, we're randomly selecting people and they're hearing it, 90% of them will be hearing it for the first time, and therefore they're part of this growth rate. So the portion who would be hearing it for the first time would be 90%. So the growth rate would be 900. We're basically imagining on a day where there are 2,000 people who know it, it's going to grow at a rate of about 900 new people. And more generally, what's happening here is our differential equation mimicking the same thing. The number of shares would be 1/2 times the number of people who know it right now. And then the portion who are hearing it for the first time would be out of 20,000 students, how many haven't heard it? And that's 20,000 minus G. So this is the number of shares. This is the fraction of people who will be hearing it for the first time. And we could rewrite this as 1 over 40,000 times G times 20,000 minus G. And now we're going to solve this differential equation. It is separable. So I am going to, let's just rewrite this in one place. If I separate the variables, I would have 1 over G times 20,000 minus G, dg, equals 1 over 40,000 dt. And we're going to integrate each side. This is done by partial fractions. So I'm going to just do that on the side. So as a side calculation, let's solve a over g plus b over 20,000 minus G equals 1 over this denominator. So if I multiply both sides, it looks like this. If I plug in G equals 20,000, I get 20,000 times B is equal to 1. So B is 1 over 20,000. If I plug in G equals 0, I get 20,000 times A from this part. This is 0, equal to 1. So A is also equal to 1 over 20,000. So going back here, and I'm going to start writing these smaller so I can squeeze them all in. This would be 1 over 20,000 over G plus 1 over 20,000 over 20,000 minus G, dG. And this is 1 over 40,000 dt. And before I integrate, I'll just notice this has the tiny fraction of 1 over 20,000, as does this, and this is 1 over 40,000. So if I multiply everything by 1 over 20,000, I get this nicer version. Where I just have 1/2 over here. So now we do antiderivatives. G is always between 0 and 20,000, so I actually don't have to worry about absolute values. I do need to remember that there's a negative here, so my antiderivative will have natural log of 20,000 minus G that I need to subtract. And here I have 1/2 t plus c. So we're done with the calculus, but we have to do quite a bit of work to solve for G. So first I'm going to use a log rule. Subtraction of logs can be rewritten as log of the quotient. And now e to the left is equal to e to the right, so they cancel over here. And I would have e to the 1/2 t plus c, which is e to the 1/2 t times e to the c. This is just an unknown constant, so I will rename it c and put it in the front. Now I will cross multiply. Well, not cross multiply, I'll multiply both sides by that denominator. And I will distribute. This is not a quick or easy process, and it's not really something you will need to do, but I think it's important to at least once see where this formula comes from. So now I'll take my two terms with g's in them and move it to the left. And I can factor out a g. So I have g of t is 20,000 e to the 1/2 t over 1. Oh, sorry. Where did my c go? I apologize for that. There should have been a c here. You probably were so confused if you're watching this. And then a C here. We move this over a little bit. And then there's a C in here, and there is a C here. So there's still a C here, and there's a C here when I move it over. There's a C here, and a C here, and a C here. And one thing I want to point out, I'm sorry about this sloppiness. You might look at something like this and say, oh, it's 20,000 times a constant. I'll just rename that C. But we have C more than once. And what we do need to honor is even though I don't know what those constants are, I do know they're in a 20,000 to 1 ratio. So I can't call them both C. That gives the illusion that they're the same. And if I call them C1 and C2, I'm losing that information about their ratio. So when the c shows up more than once, we need to leave it in. Now, if we're clever, we can try to rewrite it so it doesn't show up more than once. So this is a version of the correct answer. I am going to multiply top and bottom by 1 over c times e to the negative 1/2 t, because I don't like that c is showing up twice and that this exponential is showing up twice. So my numerator will just be the number 20,000, because c and this positive power cancel with 1 over c and this negative power. And then down in the denominator, I would have 1 over c e to the negative 1/2 t plus 1. And now we'll notice there's only one constant. So I'll rename that as c. I'm also going to switch the order in the denominator. So this is our general solution. It took a lot of steps. My hope is this form of the equation looks familiar to you. We still need to find our particular solution. We know that g of 0, let's just note e to the 0 is 1, is equal to 2. So if we multiply both sides by that denominator, we would have 20,000 equals 2 plus 2c. Divide everything by 2. 10,000 equals 1 plus c, and c equals 9,999. So our final formula here is g of t is 20,000 over 1 plus 9999 e to the negative 1/2 t power. And this is an example of a logistic formula. You've probably seen them before. Here is the most generic version of what the formula looks like. And the typical graph of one of these is that it grows slowly, then it steepens up, then it slows down again. If we cut it off early enough, right, if I were to say, just look at this portion right here, this looks like exponential growth, right? Basically a horizontal asymptote and then it gets steep. What's happening is it's like exponential growth that doesn't happen long enough. Right? Exponential growth would keep getting steeper. This is like exponential growth, but then it slows down. This horizontal asymptote that it follows is called the carrying capacity, and it corresponds to the L in that formula. It essentially represents, in the long run, what stable value are we going to hit. So what are some things to know? Lots of things can be modeled with logistic function. So spread of ideas, spread of diseases, spread of illnesses, the size of a population, if it's inhibited growth. Maybe a population grows, but it doesn't have infinite resources. It's basically going to get close to its maximum and level off. Use of a resource can be like this. There are a lot of things where this kind of function comes into play. This limiting value, as I mentioned, is called carrying capacity. If you see a formula exactly like this with a 1 plus in the denominator, you can just read it off. It'll be the numerator. Even if you see it in a different form, right? If I saw something like 40,000 over, not, let's change that, over 20 plus 61 e to the negative zero point 0.1 t. If I wanted to know the carrying capacity for this, I could just run a limit. I could say, what happens as t goes to infinity? In the long run, what's the value going to be? And what happens is we have these negative powers. So e to this huge negative power is going to be approximately 0. And the 61 doesn't really matter. So my entire denominator is roughly 20. So it's 40,000 over something that's roughly 20, and this would be 2,000. Essentially, our carrying capacity is the ratio between those two numbers. It's easiest when we have a 1 in the bottom, but you can figure it out in other cases. When we have a logistic growth with a carrying capacity of L, the differential equation can be put in this form. We might not see it in exactly this form, but we basically can write it as some constant times something that's measuring how big times something else that's measuring how far is it from the carrying capacity. Because if we get close to that carrying capacity, it slows down. If we're literally at the carrying capacity, if L is equal to P because we've hit the carrying capacity, this is 0 and our growth rate is 0. So that makes sense. A very important fact to know is, well, actually, if we look at this formula, right, if I were to graph dp dt as a function of P, it's equal to 0 at 0 and at L, and it would be an upside down parabola. By symmetry, this maximum occurs when P is halfway between 0 and L, which is L over 2. So when we have logistic growth, the maximum growth rate, the fastest growth, occurs when the size is half of the carrying capacity. And that's time independent. It doesn't matter how big it is when we started the clock. The fastest growth will be when the population is half of its maximum, half of its carrying capacity. If we have an example where the population, I'm assuming it's a population, starts above its carrying capacity, our solution to this differential equation would look like this. We would just approach it as though it were like a Newton's law of cooling problem. It's just a shifted exponential decay. And the negative exponent we're seeing here, that rate, is essentially the intrinsic growth rate. So in this case, we saw a negative 1/2. What that means is, right, imagine we weren't confined to a university of 20,000 students. Imagine that this was in some sort of universe where there were infinitely many people and we could continue spreading and spreading and spreading. So if there were uninhibited growth, right, which really isn't feasible in the long run, but if there were uninhibited growth, we would still see that 1/2, and it would grow like 2 times e to the 1/2 t. So that 1/2 is really sort of the rate at which it wants to grow, and we see that in the formula. Okay, that is it for this video.